Now let's study some quantities to describe relationship between two random variables. So let's say x and y are random variables. So they are both measurable functions from some sample space to real numbers. Okay. We can say that the expectation value of x plus y is the sum of expectation values of x and expectation value of y. Okay, but what does this really mean? Okay, according to the second definition of expectation value, we can see that this means let's try discrete case for this one. So this is what? X is a function of omega and y is a function of omega. And we have this probability, right? So we just distribute them and split the summation. We have this plus this summation. And this is just a definition of the expectation value of x and expectation value of y. Okay, so that looks easy. But what if we apply the first definition of the random variable? What does that mean? So this means we take summation over all possible values of x and summation of all possible values of y and x plus y, and probability that this random variable x takes the value of small x and random variable y takes the value small y. Okay. And what this means, I think probably we should use intersection here. Intersection. Okay, then distribute this. And we have x, y, x probability of and y, okay, and plus x, y, and the same probability. Okay, same probability. But if you look at this, here y appears only in this part, and x appears only in this part. So we can write this as sum over y okay, and similarly we have first sum over y, then sum over x. Okay, but now do you remember what this is? And what about this? These are marginal probabilities. So this is actually equal to this probability. So you sum over all possible values of y. So what's left is just x. And here what's left is just y. And these are the original definitions of the expectation value. So this is expectation value of x, and this is the expectation value of y. Okay. So in general, if we have random variables a and x and y, and constants a and b, the expectation value of linear combination of these random variables can be calculated as the linear combination of the expectation values. So in other words, this operation of taking the expectation value is a linear operator. Actually, this is very natural because expectation value is nothing more than an integral or summation, and those operations are linear operations. So naturally, expectation values are linear operators. All right. Now, recall that consider joint distribution of some continuous random variables. If this x and this y are independent, then we can split this joint distribution into the product of two density functions. If so this is independent x and y. Okay. If they are not independent, we cannot do this decomposition. Okay, if this is the case, then expectation value of the product of x and y can be split into the product of expectation values. Okay, this can be proved in the similar manner as the previous example of the sum. So just apply the original definition, and somehow you manage to calculate the marginal probabilities, then you will have this. Of course, you need to use this because we're assuming independence. Okay. And similarly, if x and y are independent, the variance of the sum of two random variables can be split into the sum of variances. Okay. Variance of the sum is sum of the variances. If x and y are independent. If they are not independent, then this doesn't hold. So okay, now we want to define covariance, which measures the correlation between two random variables. first definition. Let's say we have random variables x and y, and let's say mu x is the expectation value of x, and mu y is the expectation value of y. Then covariance, denoted as cov xy, is defined as the expectation value of this quantity. So deviation of x and from the mean, and deviation of y from its mean. Okay, so this is the covariance. What does this mean? So if you look at this inside, if x is greater than its mean, then this is positive. Okay, and if at the same time y is greater than its mean, then this is also positive. So in other words, if both are positive, the product is positive. And if both are negative, then the product is again positive. So that means if x goes up above the mean and if y goes up above the mean at the same time, then this term is positive. Okay, x, y, and also opposite happens. If x goes down below the average and at the same time if y go down below the average, then inside this is positive. Okay, so if x and y are moving or distributed in the same manner, in cooperative manner, I would say, then on average, if that happens, then the covariance is positive. Okay, so on the other hand, if they move in opposite directions, like when x goes up, y goes down, when x goes down, y goes up. If this is the case, then this will be positive number times negative number, or negative number times positive number. So on average, this covariance, these products will be negative, so the covariance will be negative value. So we say in this case, x and y are positively correlated, and in this case, x and y are negatively correlated. Okay. If we have many random variables, like x1, x2 up to xn, then we can define a matrix like this. Okay, C11, C12, C1n, Cn1, and Cnn. Okay, where each element, Cij, is defined as either variance of xi if it's diagonal. So if I and j are equal, it's variance, and otherwise it's covariance. Okay, so if x is not equal to j. Okay, so that means the diagonal, they are variance, and off diagonals, they are covariances. Okay, such a matrix is called variance covariance matrix. So we can just say covariance matrix for short. Okay. As you can see from the definition, if you swap the order of this xi and xj or xj and xi, covariance should be the same. So it's symmetric. So this is a symmetric matrix. In other words, Cij is equal to Cji, symmetric. And there is one more important property about the covariance matrix. It is semi-positive definite. Semi-positive or positive semi-definite. I don't know. Positive definite. Well, in essence, it means all the eigenvalues of covariance matrix are positive or non-negative. So that means all eigenvalues are greater than or equal to 0. Okay. Actually, the definition of positive semi-positive definite is a little bit more involved, but in essence, it means this. All eigenvalues are non-negative. So, in a sense, the variance-covariance matrix extends the concept of variance to multiple random variables. Remember, the variance of one random variable cannot be negative. Similarly, the eigenvalues of the variance-covariance matrix cannot be negative. Okay. Oh, by the way, if you remember, any real symmetric matrix like this, of course, these are all real numbers. Any real symmetric matrix has real eigenvalues. Okay, that's a theorem in linear algebra. In general, real matrix can have complex eigenvalues, but that's not the case for covariance matrix. So, therefore, we can always say, always discuss its sign, and they are non-negative, always. Okay. And related to covariance matrix, we define correlation coefficient. Okay, which is defined as covariance divided by square root of variance of x and variance of y. Okay, and you can prove that this correlation coefficient takes the values between -1 and +1. When x and y moves exactly in the same direction always, then the correlation coefficient will be exactly 1. And if they always move in opposite directions from the mean, then their correlation coefficient will be negative. Okay.